Hi guys, we're going to be working on lesson 2.11, sinusoidal functions as mathematical models. Here I'm looking at example 1 in your notes. It says, suppose that a water wheel rotates at 6 revolutions per minute. You start your stopwatch. 2 seconds later, point P on the rim of the wheel is at its greatest height. Assume that P's distance, d feet above the surface of the water, is a sinusoidal function of the number of seconds t the stopwatch reads. So they've given you a diagram with some information in it, and they've also given you some text with information in it. So the first thing we want to do is pick out the relevant information, figure out what's going on in this problem, pick out our amplitude, vertical displacement, period, and phase displacement. So looking at the text, it says that it's going 6 revolutions per minute. This is talking about the speed of rotation, which is going to talk about your period. So when it talks about revolutions, we're talking about period. If you're not aware, 1 revolution is 1 full cycle, 1 time around the circle. Anytime it talks about time, we're talking about the x-axis. So here we're talking about our phase displacement when it says 2 seconds later. So that's going to be my phase displacement. They don't say anything in the text about the y-axis, so you need to look at the diagram that's given to you. Let's look at the diagram. When they say distance above the surface of the water, they're assuming that the water is the x-axis. So if the water is the x-axis and the wheel then makes your y-axis, the height of the wheel is your y-axis. And so what we can see here is the center of the wheel. The center of the wheel is going to create that sinusoidal axis for you. And in the picture, they've labeled from the center of the circle to the water is only 6 feet. However, the radius of the wheel is 7 feet. So that 6, the distance from the water to the center, is going to be your vertical displacement. Vertical displacement is 6. And then your radius is going to be your amplitude. Radius is your amplitude. So we've got amplitude 7. Because if I rotate this, it's going to be 7 feet from the center to the top. It's also 7 feet from the center to the bottom, which is definition of amplitude. So we've got our y-axis information figured out, vertical displacement and amplitude. I've got my phase displacement of 2 seconds. And it says that's at the greatest height, which makes it a cosine wave. Cosine, because it's at the high point. And then we've got 6 revolutions per minute. So I just said 1 revolution is 1 cycle. 1 revolution is 1 cycle. And here they're saying that it's 6 revolutions per minute. So if I've got 6 revolutions per minute, okay, that's what they're giving you. But they said phase displacement is in seconds, 2 seconds. So we want this to be in seconds. So we're going to convert this. Let's convert this into seconds. We're going to take 1 minute is 60 seconds, dimensional analysis. That cancels my minutes. And then that gives me, if I reduce 1 revolution takes 10 seconds. And if 1 revolution, 1 full cycle is 10 seconds, then 10 is my period. We're going to put all of these equations in radians when we're doing word problems. So part A in the example says make a graph. We've got all of our important information. We also have a diagram that will look very similar to our graph. And now we're going to make a graph and make sure we label everything. So we've got a y-axis and an x-axis. And the y-axis, they're saying the problem is d feet, the distance above the water. So label your y-axis so that we know what it stands for. Your x-axis is going to always be time when they're talking about time. And here we've decided to measure it in seconds because because that was the phase displacement that they gave me. So if my phase displacement is 2, that's going to be my starting x value. If the period's 10, that tells me I'm going to end 10 units later, 10 seconds later, which would be 12. And remember, I want 5 critical points. And so the same thing that we did before, if we take our period divided by 4, that tells me what I'm going to go up by. So I'm going to go up by 2.5 seconds each x value. We're going to go up by 2.5 seconds. So if I go up 2.5, this is 4.5, and then 7, and then 9.5, and then we get to that 12. So that's our x-axis. Now let's look at our y-axis. We've got vertical displacement of 6. So I'm going to draw my sinusoidal axis there. We've got amplitude of 7, so we're going to go up 7 and down 7, which is going to put me at -1. And think to yourself, why is it going to go negative? Why is it going to go negative? Remember, the surface of the water is 0, and this wheel is dipping down into the water. It's picking up more water to make the wheel rotate. So it's going down 1 foot into the water, which is why we've got a negative. If we plot points, it said that 2 seconds, it was at its high point. And if this is going to rotate sinusoidally, we know the next point will be middle, then the next point will be at the low point, -1, then middle, and then high point again. And so we can sketch this sinusoid, connect the dots with a smooth curve. We've got something that looks like this. This is what's been described in the problem. So this will be a good graph for part A. Part B, they want us to create an equation out of this. Part B is an equation. Now, they told you that the output is distance. So instead of y equals, we're going to say d equals. We always start with vertical displacement first, so it'll be 6. And then we're starting at a high point, so this is a positive cosine wave, so it'll be plus. Then we've got amplitude always comes next. And then we said it was a cosine, so cosine. Period, we're putting this in radians, so remember you're going to take 2 pi divided by your period. 2 pi divided by 10, 2 pi divided by the period, and we get pi over 5 for the b value. And then x, but here we're talking about time, so t, and then minus your phase displacement, which was 2 seconds. So this would be the equation, or the mathematical model that represents the real world problem. C, when time is 7.7, is the point underwater or above water, and how far? So what we want to do here is they've given you a t, you plug it in for t. So I'm going to write down the model and plug in 7.7 in for t. And now we've got some calculator work. You want to subtract 2, put this number on pi, and make sure your calculator is in radians and type it in. So if I subtract 2, I get 5.7, so it's going to be 5.7 pi over 5. And you want to type that into your calculator, and if you do it correctly, you should get -0.33. So that is what the calculator says. We want to put it in the context of this problem. So what did we just find? We just found a distance, and we found a negative distance. So that tells me that the point is in the water, because it's below the water line. So it also means feet. So feet, distance is -0.33 feet in the water. In the water. And then part D, it says find the first positive time at which the point emerges from the water. The first positive time. So we're looking for time, and they're telling me distance. They're telling me that it is coming out of the water. And if it's coming out of the water, then that means the distance is 0. It's at the water line, because that is where it would come out of the water. So what we want to do is set our equation from part B equal to distance 0. And solve for time. Solve for time. So what we want to do first is subtract 6 to the other side, and then we want to divide by the 7. So if I subtract 6, I'm going to have negative 6. If I divide by 7, it'll be over 7. Next, we want to bring cosine to the other side. So we're going to do inverse cosine of negative 6/7. Then we want to do reciprocal of the pi over 5. So now it is 5 over pi. And last, we want to add 2 to the other side. So we've solved for t. We've isolated the t variable, time. And now we just want to evaluate this on our calculator, and we want to make sure we're in radians. So we want to start by typing in the cosine and create a general solution for this. So type in inverse cosine of negative 6/7. When you type it in, you should get 2.6 on the calculator. Remember, for cosine, that's the one we like. We can just put a plus or minus on that. So plus or minus 2.6. And we want to turn this into a general solution. So we put plus 2 pi in on it. Once we have that, we then can distribute our 5 over pi. When you do that, you're multiplying by 5 and you are dividing by pi. And what you get is 2 plus or minus 4.14 plus 5 times 2 is 10. Pi's cancel, and there's an n. So we've got it down to 2 equations, and now we want to find the times. So we're going to do negative 2 plus 4.14. Not negative 2, positive 2. Positive 2 plus 4.14, which is going to give you 6.14. So that's one equation we're going to find a list for. And then we've got 2 minus 4.14. So that would be negative 2.14. And we're going to make a list for that. If I add 10 to this, or if I subtract 10, it's negative, and I don't want negative time. It doesn't make sense. If I leave it alone, my first time is 6.14 seconds. If I add 10, it's 16.14 seconds. Over here, if I leave it alone, it's negative. Negative time doesn't make sense. If I add 10 to that, then I get 7.86. If I add 10 again, that's 17.86. And the question asked us, when is the first time the water emerges from the water? So we want to go back and look at our graph, which I just erased. And we see that at time 2, it was at the high point. Time 2 was at the high point. And so we've got these x values. Shouldn't have erased this graph. So what we had was 2, 4.5 was when it hit the middle. We've got 7 was when it went to the low point. We had 9.5 is when it hit the middle. And then it was back to 12 when we had the high point. And so you want to think about what this pebble is doing. It's starting at the high point, it's going down, and it's entering the water somewhere between 4.5 and 7. So we look at our list of times, and what time would that be? That time would be this time, 6. This is the number between 4.5 and 7. So this is where the pebble is going into the water as we watch the path on the graph. Then we want to look at our graph and see, it looks like the pebble is coming out of the water somewhere between 7 and 9. So what would that be? That would be this value here. This is where the pebble is first coming out of the water, or the point P, not the pebble, coming out. So this is the time they're looking for. This is where the point P is first emerging from the water. And that is the answer to example 1.